So it is, in fact, about 1.5 minutes after class starts. So let's get going. We just finished chapter 3 and started into chapter 4 last time. Well, I shouldn't say just finished. Last time we actually started into chapter 4 and got a little ways in there. We worked an Atwood machine and a couple other things. I was able to show you guys the formula for weight using the idea that basically weight is the word we give the gravitational attraction between the planet and the object on which the planet is acting gravitationally. And we used the idea of free fall, what we had learned in chapter 2 and then used again in chapter 3 to know what the acceleration of a object in free fall was. And from that, we were able to put together the formula for the weight, which turns out to be weight is equal to the object's mass in kilograms times the gravitational acceleration that it experiences. And of course, that gravitational acceleration, you don't know this yet. You will know when we cover gravity, but the gravitational acceleration depends not only on how massive the planet is, but also on how far you are away from the center of the planet. It turns out that even if you take into account the lowest point on the Earth which would be the bottom of the Marianas Trench, and the highest point on Earth, which would be the top of Mount Everest, even in looking at those two extremes, the difference between the gravitational acceleration at the bottom of Marianas Trench, which should be the highest gravitational acceleration, and the gravitational acceleration at the top of Mount Everest, which should be the lowest, it turns out that they only differ by a couple of percent, so it's really not that big a deal to worry too terribly much about how the gravitational acceleration changes as a function of altitude, unless you're really looking for highly precise information, like 2 or 3 decimal places. Well, actually, let's say 3 decimal places in terms of the distance traveled, time taken, or the velocity. If you start to get to 3 or more decimal places, then yeah, you're going to have to account for it. But at 2 decimal places, g equals 9.80 is plenty good. So we did do that. Now I'm going to go on into solving some more problems. The whole crux of this thing is we learn Newton's laws, the first of which says that an object in motion tends to stay in that state of motion unless acted upon by a net external force. So, for instance, if you look at, let's say, my Rubik's Cube that's sitting here on my desk, you look at it and say, well, I know there's one force acting on that Rubik's Cube, and that's the Earth's gravity. And then you'd realize, well, wait a second, that's a kind of special force in that the Earth is acting on my Rubik's Cube, but the Earth isn't touching my Rubik's Cube. It's sitting on a shelf, which is on a bookshelf, which is sitting on a floor, which is a good couple feet above the Earth's ground level. So it's not even touching the Earth. So that's one of those forces that we call action at a distance. And I bring that up specifically because when you're doing a free body diagram, to apply Newton's second law of motion, you need to draw a free body diagram for the objects that you're studying. But what you do is you one by one go through every object that the body that you're doing the free body diagram for is touching. So, for instance, in the case of my Rubik's Cube, the only thing it's really touching is the desk. And once you get through all the things that it's touching, then you have to look for a special class of forces, and those are forces that act at a distance. Gravity being the one that we're talking about right now. And it should be obvious that you're seeing that, in fact, it is action at a distance because, like I said, the Rubik's Cube is not touching the Earth, yet the Earth is reaching up and grabbing it. So there's a couple forces like that. It turns out that the gravitational force is like that, the electric force is like that, the magnetic force is like that, the strong nuclear force is like that, and the weak nuclear force is like that. Now, that's the 5 major forces. Now, thanks to Maxwell, we've decided and understood that the electric and magnetic force are just two sides of the same coin. In some sense, you can combine the nuclear force with those two for the standard model. And in that sense, there's sort of a state in which the electric force, the magnetic force, and the strong nuclear force are different sides of the same coin, but that still leaves gravity and the weak nuclear force. And we haven't really figured out a way to unify those, but ideally we would like to. So for right now, you just have to take into account that the action at a distance forces really are just gravity. You won't study magnetism or the electric force till the second semester of this course. You're not going to study the nuclear force at all. So you really don't have to worry about gravity. So everything that's touching the object has the potential to put a force on it. Therefore, you should draw a free body diagram, including those forces, and then go for gravity. Then go for action at distance. I'm sorry, I don't know what's going on. I just started yawning. Have not yawned at all the whole day, but all of a sudden I'm yawning. So I don't know. I apologize for, for it being a hassle. So now that we've sort of explained that, let's get started on some examples. So I'm going to start off by sharing my iPad screen with you guys. And I've only got a couple of examples written up, but they're kind of important ones. So let's go ahead and get those started. Let me start by sharing my screen. Oh man, great. Now my nose is acting up too. So yeah, that's great too. Yay. All right. So it should come up any second now. Okay. So the first problem we're working says what average force can accelerate a 1,500 kilogram car from rest to 115 kilometers per hour in a distance of 60.0 meters. So here's what we're going to do. We're going to solve this problem accordingly. So first off, what we know is since it started from rest, we know that V initial is equal to 0. We know that V final is equal to 115.0. Notice the 0 is not a sig fig, kilometers per hour. And we really need that in meters per second. So what I'm going to do is realize that 1 hour is equal to 3,600 seconds, and that 1 kilometer is equal to 1,000 meters. So basically what we're going to do is take that 115 and divide it by 3.6. So 115 divided by 3.6 gives me 31.94 meters per second. Now that had three sig figs. I'm now giving 5 digits, so two of those are not significant. We're good to go on that. We also know that it has a mass m is equal to 1500.0 kilograms. That last zero being not significant, so that gives us 4 sig figs. And we also know that in a distance of 60 meters, this acceleration takes place. So I'm going to use x minus x0 is equal to 60.0 meters. Now I could have just said x0 is equal to 0 and x is equal to 60.0 meters. Either one of those would work just fine. The main thing I was shooting for is I know that I have a final velocity, I know that I have initial velocity, and I know that I'm asked for a force. And since I'm asked for a force to accelerate something, I'm thinking in terms of Newton's second law, which says the summation of forces is equal to mass times acceleration, which of course you get for each dimension. You get summation of forces in the x direction equals mass times acceleration in the x direction, then another one for the y, and another one for the z. This all seems one-dimensional motion, so we're probably just going to use one of those forms. And the vectorness of it, since it's in one dimension, is just an association with a positive or negative. But I clearly need an acceleration to get the force. And in fact, what makes me think of what acceleration or how I'm going to get the acceleration is one of our kinematic equations that says v squared is equal to v initial squared plus 2a times x minus x0. So that's what I'm going to use to figure out the acceleration. Let me start off by calculating the acceleration, and then I'll go from there and calculate the force. So according to this equation, the acceleration should be equal to v squared minus v initial squared over 2 times x minus x0. So that's an equation for the acceleration. Using that, I'm going to say A is equal to V squared. V is the final velocity, and we found out that that was 31.944 meters per second squared minus 0.00 meters per second squared, and all that will be divided by 2 times x minus x0 is 60.0 meters. So if I square the 31.944, I get 1020.44. Now I'm going to divide that by parentheses 2 times 60, close parentheses, and that gives me 8.50 uh, 37. And that's meters per second every second. Notice the numerator is meters squared per second squared, and then you're dividing it by a meter. So that's how we get meters per second per second. And in this case, we had 3 sig figs on top and 3 sig figs on bottom. So the 3 and the 7 are not sig figs. Now we just use the summation of the forces in the x direction is equal to mass times acceleration in the x direction, and that gives us the total force. Now, we're calling it the sum of all the forces, but in reality, what we're looking at here is we're just trying to figure out what total force is required to accelerate this thing this way. So we're really solving for that. In fact, if there was a friction force or an air resistance force of, say, 200 newtons, and we still wanted that same acceleration, we're probably going to have to add another 200 newtons to it. So I'm just solving it as if it's the only force, and we're calling that the sum of the forces. Now it's going to be equal to m times a, which is 1500.0 kilograms, times the acceleration, which is 8.5037, and that's meters per second every second. And that gives us 12,755.6 newtons is the unit. Now we had 3 sig figs there, so really this 5, 5, and the 6 are not sig figs. So the force that we actually needed, the net average force that we needed, should be 1.28 times 10 to the fourth newtons. And that's really the way you're supposed to do this, is basically if you don't have enough sig figs to go all the way from uh, sig figs to the actual true decimal place, then you need to use scientific notation or use a prefix. Like we could convert this to 12.8 kilonewtons. That would work as well. But the main thing is by only showing 3 digits, we're saying that the 3 are all significant. We could also write this as 12.8. Actually, I would leave off that 8 and write it as 12.756 kilonewtons. So that would be acceptable too. So at least with anything you turn into me, if you have underbars or underlines under the numbers, I'll understand that that means that those are not interpreted as significant figures. Anybody have any questions on that? Okay. Well, this is a conceptual example, and it's very much a conceptual example. There's 2 conceptual examples, in fact, in your book that I think are important. This is one of them, and I think the best way to answer this is for me to explain it to you, and then you think it over. And by me you having it on recording here, you can think back about it by, logging back in and loading the video and watching it up until this point. But basically, it's asking what makes a car go forward. So a lot of people would just say, quite sensibly, well, I push the accelerator, I push the gas pedal. And that's right. You're actually doing that, but that's not actually what's applying a force to the car to make it accelerate. So when they're saying what makes a car go forward, they're really trying to ask you what force actually applied where and on what is actually acting on the car to make it go forward. So what really happens when you do hit the accelerator or the gas pedal is basically one, we're assuming that you already have it in gear and that you were possibly had your foot on the brake to hold it still for a second. You put it in drive or maybe first gear if you're driving a stick shift and you still got the clutch in, that sort of thing. But the main thing is when you hit the accelerator, that makes more fuel come into the piston chambers, and then they immediately call for an explosion because what's going to happen is the piston chamber has going to is going to take the piston and it's going to push down and start to compress the gas. And just as it gets to the very tightest compression it can, assuming it's a gas engine as opposed to a diesel engine, right as it closes and gets as close as it can to the end of the piston chamber and to where the spark plug is, the spark plug fires and there's an explosion. That explosion ignites the gas air mixture that causes the power stroke that pushes the piston down. That piston being pushed down actually rotates a shaft that is the same shaft that goes to your transmission and then goes on to your drive shaft, which often, at least in trucks, goes straight from the transmission to the rear, what they call hog's head or differential. So if you look on a rear axle vehicle, you'll see a big ballish shaped thing on the axle, either in the middle or off to one side a little bit. That's called a differential, and it's a bunch of gears in there that basically, well, if you've ever ridden a go-kart, they usually don't have differentials. So when you go to take a turn, you'll see that it tears up grass on one side. And that's because when you're actually making a turn, the wheel on the inside is supposed to go slower than the wheel on the outside because they have different radiuses of curvature for their paths, and therefore the inside wheel has to go a little slower than the outside wheel. The differential makes all that work out so that the inside wheel turns exactly as much as it's supposed to, and the outside wheel turns exactly as much as it's supposed to. But either way, that rotates, and then that causes the rear axle, one side or both, depending on whether you got posi track, but usually one side, and it tries to rotate the rear tire in a way like this so that the tire would then push backwards on the earth's surface, which is the road or the gravel or whatever you're on. So we've now gotten to the point where the pushing of the gas has resulted in a rear wheel trying to rotate forward. If that engine is so powerful and you've pushed so much force or so much gas in it that it's so powerful that the friction can't stop that tire, then the tire is just going to spin out and maybe move it a little bit forward. But in a normal situation, you're supposed to hit that gas and then the tire tries to rotate, but it can't because the friction, called static friction, is high enough where it won't slip with respect to the road. So those two stay not in motion relative to each other, but in sitting still with respect to each other. And since it does that, the bottom of the tire is actually pushed forward by the earth. So the earth or the road or the gravel, whatever you're sitting on, pushing the tire forward is really what makes the car go forward. Anybody have any questions on that? It's not necessarily the most sensible way to think or the most reasonable way. It's in other words, it's not obvious that you should be thinking that way, but it turns out that that is the correct way to work out the details. So, any questions on that one? The other one is a question. I'm going to read it verbatim. I make up a question just like this in my classes in the past, only this one's a very specific one that has a neat little historical reference or whatever. But the other conceptual example is this. And they have a picture. This is figure 412 in your textbook, conceptual example 4.5. So I'm going to say conceptual example. Whoa, I actually screwed up a little bit on my letter there. This is 4-5. And what it says is Michelangelo's assistant has been assigned the task of moving a block of marble using a sled. It says see figure 412. He says to his boss, when I exert a force on the sled exerts an equal but opposite force backward. So how could I ever start moving? No matter how hard I pull, the backwards reaction force always equals my forward force. So the net force must be zero. I'll never be able to move this load. Is he correct? Let me read that again to you. Michelangelo's assistant has been assigned the task of moving a block of marble using a sled. He says to his boss, when I exert a forward force on the sled exerts an equal and opposite force backwards. So how can I ever start it moving? No matter how hard I pull, the backward reaction force always equals my force. So the net force must be zero. I'll never be able to move this load. Is he correct? Anybody have an idea on that one other than just reading it? Because, obviously that sort of defeats the purpose. It's a bit of nuance, so it's perfectly understandable if you don't necessarily get it right now. But what you're supposed to understand, especially the way I write it, so when I say Newton's third law, which is what they're using here, Newton's third law, so I'll say N3L is basically the force on object A as a result of object B, or you could say the force on A due to object B is equal to the negative of the force on object B as a result of object A. That's Newton's third law. So that seems completely consistent where we say when I exert a forward force on the sled exerts an equal and opposite force backwards. Notice they stop the sentence there though. When I exert a forward force on the sled exerts an an equal and opposite force backwards. They don't say anything on that sentence after that. They just start a new sentence and says, "So how can I ever start it moving? No matter how hard I pull, the backward reaction force always equals my forward force, so the net force must be zero." Is that part of the question right? They said, "So the net force must be zero." Is that part true? The forward force is equal and opposite. Got the person came in. Hold on. So the forward force is equal and opposite to the backward force. But again, I'm stopping right there. So I ask you, uh, it says, so the net force must be zero. Did anybody come up with an idea of whether that's true or not? I'm going to turn my chat on in case somebody chatted the right answer. I do not see anyone. So anyone have any questions on that? All right. Well, I'm going to go ahead. This is also not the most obvious thing to understand. So, when Michelangelo's assistant says this, he's absolutely right. Like I said, the forward force is equal and opposite to the backward force. That is what Newton's third law says. But something else Newton's third law says, notice this, the force on object A due to object B is equal to the force on object B due to object A. So the problem here is that Michelangelo's assistant is picturing the two forces acting on the same thing. Action reaction pairs always act on different objects. So it makes no sense to add two forces, one of which is acting on A and the other one's acting on B. The only reason you'd ever want to add two forces is when they're acting on the same object. Okay. So what he's saying is very easy to confuse you because it does seem like you're pushing, let's say, with a 400 Newton force forward and it's pulling backwards with a 400 Newton force. That does seem a little bit like the 400 minus 400 would give you zero, but you put the 400 newtons, say, on the big sled pulling the block of granite, and it put that force, that 400 newtons backwards on you. So the force on the sled is what matters in terms of getting the sled to accelerate, not the force on you. So the answer is yes, it will accelerate. No, he's not correct. The reason he's not correct is that action reaction pairs act on different objects. So I'm just going to say action reaction forces act ooh, on different objects. So they shouldn't be added. So hopefully that helps you guys understand that a little bit. Uh, those two forces, the action reaction pair, like it would actually help you a lot to think a little bit about each force you can think of. What's the action reaction pair? So right now the Earth is pulling down on me with a force of 255 pounds, say, right? What is the action reaction pair to that? So if you call the force acting on me the action is 255 pounds downward on me. So can anybody tell me what the reaction force is? We're looking for something that would be acting upward, would still have a force of 255 pounds, but I'm not telling you what it would be acting on. Anyone?
Is it the normal force?
Uh, that is the most common answer. It turns out not to be right, but thank you for trying. That's way typical. That's exactly what people expect. But remember, the forces not only are equal and opposite, but they're operating or acting on equal and opposite things. So when I say the gravity of the Earth is pulling down on me at 255 pounds, that means I'm pulling up on the Earth at 255 pounds. That's the action reaction pair. But it's totally expected for people to think the normal force because clearly the normal force is acting up on me with the force of 255 pounds. If it didn't, the floor would be failing or whatever I'm sitting on would be failing. So it's perfectly reasonable to think that. But you got to remember that it's the thing that causes the force acting on the thing, and then they just reverse roles like that. So uh, Earth pulls me down, so I pull Earth up. So notice how we just twist the things from the force on me due to Earth becomes the force on Earth due to me. Does that help anyone? That makes sense, Brianna? I think that was Brianna that answered that.
Yeah, that makes sense.
Gotcha. Okay. But yeah, that is one of the more weird or difficult concepts to get through to students in general. So don't feel bad, but now hopefully you know. And do think about the conceptual questions and the misconceptual questions of that sort of stuff that they have at the end of the chapters. Now that we've done that, I'm going to work some more problems that are more related to, for instance, uh, Newton's second law. So let's move on again. This is example. I called that one 1, 4, 5. Technically, this conceptual example that I just did came after it. I just wrote it before because I didn't leave enough room. But I'm going to go ahead and call this example 4, 6 because it's essentially the same example as the book has, but I'm trying to not violate copyright restrictions. And I'm trying to do that by maybe changing the question around, hopefully enough. And anyways, so what we have here is a box, or specifically a 10.0 kilogram box, rests on a level surface. Okay, that's what we have so far. A, what are its weight, W, and the normal force, N, on the box? So that's the first part of the question. The second part of the question, if a child whose weight is 30.0 newtons sits on the box, what are the box's weight, W, and the normal force? Okay. And then part C, if an adult walks in and uses a rope to lift up on the box with a force of 30.0 newtons, what will be W and N? Note, the child is gone. In other words, we're not leaving the child on here the whole time. So this is sort of exploring the idea of the normal force. So remember, we can sort of picture this like the back of my hand is, say, the top of a table, and we know the force, one force acting on this Rubik's cube is, for instance, the force of gravity, and the name of the force of gravity that we often give objects is its weight. So the weight is acting downward on this Rubik's cube. Now, what we realize is Newton's first law says an object in motion tends to stay in that state of motion unless acted upon by a net external force. What we see is this object is sitting still, and then I wait, part of a second or so, and it's still sitting still, and I wait another part of a second, it's still sitting still. So if you have something sitting still for an extended period of time as opposed to an instant, then that means its acceleration is in fact zero, and therefore its velocity is staying the same. So this is an object that fits the criteria of Newton's first law. An object in motion stays in that state of motion unless acted upon by a net external force. Since this one is staying in that state of motion, we can conclude that the net force acting on the Rubik's Cube is zero. Well, if the only force we know of acting on the Rubik's Cube is the weight, it can't be zero. Therefore, we have to conclude there must be another force that, in this case, has to be pointing upward since the weight points downward, and it has to be equal in magnitude to the weight. So that force is what we call our normal force. Now, what we're doing is looking at what happens when we do different things. How does the normal force change? So let me show you the solution. So for starters, we're using the equation weight is equal to mg. That's going to be the formula for weight in each case. And then we're going to use the free body diagrams to make sense of each of the parts. So I'm going to go ahead and say this is 10.0 kilograms times 9.80 meters per second every second, which gives me 98.0 newtons. And of course, that acts downward. In fact, I can tell you that you probably have reached the conclusion that the weight should be the same in all three cases, and it is. Okay, the weight will be 98.0 newtons. So obviously, that acts down in all three parts. So, part A, I'm going to start off by drawing a free body diagram. What we have is the 10.0 kilogram box. I'm going to say that we have a axis, let's see, x-axis pointing to the right, and I'm going to say that there is a y-axis pointing up, and what I know is there is a weight acting downward, so I'm going to use that as red, since red like a stoplight, and therefore this is a what I would call a negative force, meaning its magnitude is 98 newtons, but it points in the negative y direction. So weight is equal to 98.0 newtons. And then acting in the vertical direction, I'm going to say is a force N, and that acts in the positive direction. So the summation of the forces in the y direction equals mass times acceleration in the y direction. But we're not told anything like, hey, once these forces are applied, the box is going to jump off the surface, or it's going to start digging into the surface, or anything like that. So we must make the conclusion that clearly there's no motion going on in the vertical direction. And no motion and still no motion means the acceleration is zero. So I'm going to put a zero there. And now we get that N plus, remember the left side of Newton's second law is always the sum of all the forces. You're adding them. But in this case, the y component of the weight is a negative. So I'll say plus negative 98.0 newtons is equal to zero. And this gives us that N is equal to 98.0 newtons, and W is equal to 98.0 newtons. So there's one answer, and here's the other. So that's part A. Now we're going to try part B. And in this case, we again have a coordinate system. I'm going to draw it here this time. Let's say that's our y-axis. Let's say that's our x-axis. This is a 10.0 kilogram box sitting here. But in addition to that, we have a small child's weight, and that is the weight of the child is equal to 30.0 newtons. We also have the weight of the box, which is W equals 98.0 newtons. And then we also have in the upward direction a normal force N. Notice your book tends to use F and then subscripts it in. I almost always just use straight N. Okay. Your book also uses a capital F and then subscripts it with a little fancy curly F for friction. I usually just use the curly F for friction. So just keep that in mind. Now we're going to do the same thing we did before. The summation of the forces in the y direction equals mass times acceleration in the y direction. But again, the acceleration in the y direction should be zero because they didn't tell us anything like the thing's going to be jumping off the surface or digging into the surface. Now, from that, what I get is n plus negative 30.0, 30.0 newtons plus negative 98.0 newtons is equal to zero. So we get that N is in fact equal to 128.0 newtons. That's the normal force. And we also get that the weight is equal to 98.0 newtons. That's that one. Any questions on that? Now I'm going to do point C or part C again. This time someone's lifting up on the box instead of an extra weight being put on top of the box. Again, we're hopefully seeing some definite facts about the normal force. I'm going to put it over here just to make more room for it. So there's my y-axis. There's my x-axis. There's my 10.0 kilogram box. Now, again, I'm going to have an upward force that in this case is the normal force, but I'm also going to have the force that the adult puts on it, and that force is 30.0 newtons. In addition to that, we have the weight, which is 98.0 newtons. We have now the summation of the forces in the y direction equals mass times acceleration in the y direction. But again, the acceleration in the y direction is zero. So I end up getting n plus positive 30.0 newtons plus negative 98.0 newtons is equal to zero. And because of this, we can now say that n must be equal. It's going to go over to the other side, become 98, and then we're going to subtract 30 from that. So that'd be 68.0 newtons. And that's our new normal force. And then the weight is equal to 98.0 newtons. And that is the weight. So you can see the weight in all three cases was 98 newtons, but the normal force was just equal to the weight in part A. In part B, when someone sat on top of the box, that made the floor apply bigger force upward on the 10 kilogram box to account for that extra 30 newtons. So the normal force, instead of being 98, turned out to be 98 plus 30, which gave us 128 newtons. Also, if you actually pull up on the box, then the floor doesn't have to supply as much force right there on the box. So in that case, we ended up getting a normal force of 68 newtons because that's 98 minus 30. Anybody have any questions on that? All right. Well, there's some more neat problems to be solved. I think they're pretty straightforward. Like they take that same sort of box scenario and they say, what happens when a person pulls upward on the box with a force equal to or greater than the box's weight and stuff like that. I think you can immediately tell what you're doing with that one. In this case, we actually have a not equal to zero, so you can actually calculate an acceleration unless the two forces exactly equal each other. But if one force exceeds the other, then that force can actually exceed it and cause an acceleration. So that's example 4.7. I'm skipping it. I think the more important thing to do would be like an elevator problem as well as a problem associated with an inclined plane. So I'm going to jump to another example. Let's call this one example 4.8. Okay. Now, in this one, it says a 70.0 kilogram boy descends in an elevator that briefly that briefly accelerates downward at 0.30 G. So again, like I did last class, when you use this G, this doesn't mean 0.30 grams. This means the acceleration is 0.30 times 9.8. Okay, so downward at 3 grams. Uh, the boy stands on a bathroom scale during this process, and the scale reads in kilograms. So it's a mass scale as opposed to a weight scale. So part A, during the acceleration, uh, what is the boy's weight and what does the scale read? What is the boy's weight and what does the scale read? And then part B, they want to know what does the scale read when the elevator descends at a constant speed? Descends at a constant rate of oh, 2.13 meters per second. Okay, so there's our problem. Let's see how we go about solving it. So what we really need here is the summation of forces in the y direction equals mass times acceleration in the y direction. For part A, I'm going to draw a diagram, but I should record some information. So for instance, I have the mass of the boy is 70.0 kilograms. I have the acceleration is downward and it's equal to 0.30 g, which equals 9.8 times zero point 0.3. That's 2.94 meters per second every second. Okay. So let's draw our free body diagram. I'm first going to just draw a regular diagram, and I'm going to include my coordinate system. So here's my y-axis pointing down, pointing up, excuse me. There's my x-axis pointing up. What we're going to have here is a scale, which I might draw this way. And you could imagine it having something like this. And then there's a little plate right here for the person to stand on. And then on that is the boy standing like that. Okay. Now that's what's going on inside of the elevator. And what I'm going to do is reduce that to a free body diagram so it's a little less complicated. And I'm going to show the acceleration as best I can, but I don't want to put it on the same diagram because that gets people into this idea of thinking that you can add accelerations and forces, and they're not the same quantities, so you can't do that. But what I do have right here is a mass m that we know. Okay, I have my x-axis this way, my y-axis this way. Now, what the forces are on it are the object's weight, which is the attraction that the Earth has for it or whatever planet it's sitting on, and that weight is equal to m times g, which is 70 times 9.80. That gives me 686.0 newtons. That's the weight. Now, the scale applies an upward force on the person, and that force is the scale reading, so I'll write it as F sub S, meaning the force that the scale reads. And that actually is going to come out to be F sub S times or let's say F sub S divided by 9.8. So I will write it as F sub S is the force. Actually, I'll leave it at that. And then I'll say that the scale reads F sub S divided by G. Okay, so that's key to understand. Now, what we're talking about here is that there is, in fact, an acceleration A downward, and that acceleration is 2.94 meters per second. So I can now take the summation of the forces in the y direction is equal to mass times acceleration in the y direction. And from this, I'm going to see that F sub scale is pointing up minus 686.0 newtons is acting downward. And that is all equal to 70.0 kilograms times the acceleration, which in this case, the acceleration is going to be downward. So I have to call it negative 2.94 meters per second. And now all I have to do is solve for F sub S and then divide it by G to get the kilogram reading. So I ultimately see that it's going to be F sub S is equal to 686 newtons. Notice when I pull it to the right hand side, it becomes plus, or actually I could also write this as plus with a negative number there, just reminding you that the left hand side always has addition in Newton's second law. So that's one way of thinking about it. But I'm also going to take this 70 times 2.94, and that gives me 205.8, but that's negative, so it'll be minus 205.8 newtons. And that obviously is not a sig fig, and the point zero that would come after the 686 is not a significant fig. So I'm going to do 686.0 minus 205.8, and that's going to give me 480.2 with the 2 not being significant, and that's newtons. So the scale will say 480.2 newtons divided by 9.80 meters per second. So we get scale reading is equal to 480.2 divided by 9.80 is 49.00 kilograms. So what we've discovered here is because the elevator is actually accelerating downward at zero point 0.3 g, the person whose weight is 70 kilograms appears to only weigh 49.0 kilograms. And that's because normally the scale is acting just like the floor of the elevator and therefore has to hold up our entire weight. But if the floor of the elevator is falling downward in such a way that it's accelerating, then it only has to compensate for the zero point 0.7 of the 9.8 instead of the full 9.8. So gravity is pulling on it the full 9.8 times the 70 kilograms, but the force that holds it up, the normal force, is allowing zero point 0.3 of that 9.80 to continue to speed up that way. So he's only fighting off the remaining 0.70 part of the G. And that's why we get 49.0 kilograms rather than 70.0. So during the acceleration, what is the weight and what does the scale read? We just got the scale reading, and of course, the weight we said was 686.0 newtons, and that zero is not significant. I've mixed up the colors a little bit just to let them stand out. That's part A. Part B, what does the scale read when the elevator descends at a constant rate of 2.13? When the acceleration is zero, you don't have any problems going on, so that you end up getting for part B, you just have a free body diagram that looks like this. There's my y-axis. There's my x-axis. There's my scale. And in this case, we have no acceleration. So we get the summation forces in the y direction equals mass times acceleration in the y direction. That's zero. Therefore, we get F scale minus 686.0 newtons is equal to zero. So this gives us F scale is equal to 686.0 newtons. Therefore, the scale reading, which is supposed to be 686 divided by 9.8, 686 divided by 9.80 gives me 70.0 kilograms, which is exactly what we expect because the object or the person, the boy, weighed 70 kilograms. Anybody have any questions on that one? All right, so that is a case that you can work out. Now, if you notice, I have the acceleration pointing downward in part A, therefore I had to call the acceleration negative 2.94. You can also consider the same problem this time with the elevator accelerating up at 0.3 g, in which case the A would be positive 2.94. And if you do that, I think you'll find that you get quite a bit bigger than 70 kilograms for the scale reading. So that's something to think about. I think you'll have plenty of time to do that kind of stuff when you're actually working on your homeworks and your practice tests, which I want to remind everybody I've moved your online test. It's going to happen this week. So I'll put up the practice test tonight and you'll have up until Sunday night at 11:59 to complete the practice test as many times as you want and then to do the actual online test uh, up to, I think I gave y'all 3 times. Sometimes I give you 4, sometimes I give you 5, but I think this time it's just 3 attempts. So all of those are due by Sunday at 11:59 p.m. Don't miss it, or you'll either possibly be dropped or you'll lose points on your test, that sort of thing. Uh, Now, next week is the actual face-to-face test. So you'll have to find somebody to proctor you or some way to get proctored at the testing center, find out what kind of appointments you need to make or whatever, because Wednesday is the planned day, like for my face-to-face class. So you could actually come in and take it with them. But the main thing is you've got to get it done sometime next week. That is an option. You can use the time that I do it with my Wednesday classes. That would be fine. But you just got to let me know and make sure. Okay. All right. Let's go on to another example. Now, this one's going to be like the Atwood machine we did last time, but this time I'm going to put it on an inclined plane. Uh, your book does example 4.9. I think that's pretty straightforward. I don't think y'all are going to have any real issues with that one. So I don't think that's quite as critical for you guys to see me do that as it is to see me do this one that's getting ready to happen. So let me do it. I'm going to draw an inclined plane. So here's my inclined plane. Okay. And that inclined plane is going to be at an angle of, let's say, 30.0 degrees. And I am going to put a box on the inclined plane. And the box has a mass, little m, equals 7.00 kilograms. Now I'm going to affix a wire or a string to the box so that it can run parallel to the incline and then run into a pulley that's mounted at the end of the incline. And then hanging from the other side is a big mass. M is equal to 50.0 kilograms. Okay. What I would like to figure out is what is the acceleration and what is the tension in the rope. Okay. So this is just like the Atwood machine. I'm trying to show you, of course, that this angle and this angle are parallel. So we're not having any string lifting up on the box or pushing down on the box. And when I say up and down, I mean perpendicular to the inclined surface, not vertical and vertical downward, but literally perpendicular to the inclined plane. So in order to do this, just like I did with the Atwood machine, we draw a free body diagram for the left one, then we draw a free body diagram for the right one. I'm going to assume the pulley is frictionless and massless. So that means the two tensions are going to be the same. The reason being, if you think about the tension right here pulling this 7 kilogram one up, it only has to pull the 7 kilogram box up. And if there was any friction, it would have to deal with that. But this is all frictionless. Whereas if you think about the tension over here, this tension would have to pull the 7 kilogram box up, but it also has to rotate this pulley that could be heavy. It also has to rotate this pulley, which could have friction. But since it's not heavy, it in fact is massless, then the tension on the right side must equal the tension on the left. So we'll say T left equals T right is what we're using here. And hopefully y'all understood my reasoning for that. So now what I'm going to do is I'm going to draw a tilted coordinate system. Okay. That's my X prime axis. And then perpendicular to that is my Y prime axis. Now, what I have here is a mass, oops, is a mass of 7.00 kilograms. Okay. Now, I have a force associated with that, that is the actual weight of the box. And that weight is equal to 7.00 kilograms times 9.80 meters per second, which gives me, I think that's 696. Let's see, 7 times 9.8, 680, or 68.6. Sorry about that. 68.6 newtons. Now, here's the little bit that's a tricky part. We've got to figure out because I need to break this weight vector into components that are parallel to the y prime axis and parallel to the x prime axis. This part right here is w sub y prime, and then this part right here is w sub x prime. That's the component parallel to the incline, whereas the y prime is perpendicular to the incline. Now, in addition to that, we have the normal force N acting right there. Now, we also have another blue force acting, and that blue force is the tension in the string. If you happen to be on the 5 kilogram box, you're thinking, oh, that neat little string is pulling me up. Therefore, that's why we think of it as a tension that's pulling up the incline. Okay. Now, what we had here with this inclined plane is this angle right here. This angle, even though I didn't draw it big enough, is supposed to be 30 degrees. Now, if you look at that as a right triangle, then you can see that this angle right here is the 30 degrees. This is the 90. So can anybody tell me what this angle is? So this one's 30. This one's 90. What must this angle be? Very good, John. He said that's 60 degrees. That's right, and that's because it's a complementary angle. We know that complementary angles are the two angles on a right triangle other than the 90 degrees. Now, if you look, this y-axis right here, that's supposed to be perpendicular to this x-axis as well. So these two are perpendicular, and we just found that this angle is 60. So what do you think this angle is? John again, yes. So because the two add up to give you 90 and 160, the other one has to be 30. So I'm going to write this in here so that you understand that this is 30.0 degrees. Now that's something that's going to be coming back to get you uh, the whole semester. Okay. And not only this semester, but next semester as well. We're not going to be able to just, forget this information later on because we're going to have uh, triangles like this frequently. So this angle is 30.0 degrees. And now we can use that to figure out that W sub Y prime has got to equal 68.6 newtons times cosine 30.0 degrees, and it's got to be negative, so I'll put the negative on there. So 68.6 times cosine 30. That gives me 59.41. I'll say 409 newtons, and that's negative, of course. And we also say that Wx prime would be equal. That one's also negative, so I'm forcing that negative sign there. Newtons. And just in case it looks a little messy later, this one's going to be times 30 point, or sine of 30.0. Therefore, I'm going to get 68.6 times the sine of 30. And this one gives me negative 34.300 newtons. So that's those two forces. Okay. Now, you don't necessarily need the normal force for this problem. We would need the normal force if we had friction, but I've avoided friction so far. We're not supposed to learn about friction until next chapter, so we don't have to deal with friction. But just so you'll understand that the normal force, as we saw in the previous example, is not just the weight. For instance, when we added a kid on top of it, it was the weight plus the weight of the kid. Uh, when we had a grown up lifting up on the box, it was the weight minus the force that the grown up applied to it. Here's another case where the weight is not going to be equal to the normal force, and the way we see that is using the summation of the forces in the y prime direction is equal to mass times acceleration in the y prime direction. But again, we're not expecting this box to bounce up and down on the incline, so the acceleration in the y direction is equal to zero for this one. Therefore, what we get is the normal force minus Wy, which we'll say plus negative 59.409 newtons, is equal to zero. So we get that the normal force is actually 59.409 newtons. So we see the normal force is actually not the weight. In this case, it turned out to be the y component of the weight. But the main thing is it's not the weight. Okay? We didn't need to do that, but like I said, I just wanted to show you that. Now I've got to do the summation of forces in the x direction. So the summation of the forces in the x prime direction is equal to mass times acceleration in the x prime direction. In this case, we do expect, notice I put a 50 kilogram mass on the other side and a 7 on this one. So it should be ample mass to pull the little mass up the incline. So that's why I made the upward up the incline as the positive direction so I would get positive answers. So the forces in the x direction are just the tension T plus the omega, or excuse me, the Wx prime, which is a negative force of 34.300 newtons, and that's equal to 7.00 kilograms times A. Now, if I move this box, if I were to, for instance, pull the box on the right down 1 inch, then the box on the left would go up 1 inch unless the string stretched or unless the string got slack. We're going to ignore the options of the string getting slack or the string stretching. Okay. Now that we've done that, we can see that the X motion, or in this case, the X prime motion up the incline, if that's 1 inch, then the X prime goes down 1 inch on the right hand side. So that shows that a position of the 7 kilogram mass acts just like the position of the 50 kilogram mass. Now, if you also consider that it moves 1 inch in 1 second, then what you'll find out is the other one will move 1 inch in 1 second. So that tells us the velocities behave the same. And if it moved 1 inch in the first second and 2 inches in the second second, you'd find that the other one does the same thing. So that tells us the accelerations are the same. So as long as I keep the x prime axis, which I pointed up the incline, as long as I keep positive associated with that direction, then the acceleration on the right will be the acceleration on the left. So that incline showing the x-axis going up it, if I followed that over the pulley, it would show the going down on the right is the same as going up on the left. So that's what I'm going to do for my free body diagram for the object on the left. So here's my axis. I pointed the x prime down. Now, all of this is just to keep me from having to make another equation to relate the acceleration on the left to the acceleration on the right. By choosing it this way, the acceleration on the left and right are equal to each other by default. In this case, we have a mass, and this mass is 50.0 kilograms. Now, that has a weight of 490. Let's double check that. 9.8 times 50 is 490. So it has a weight this time in the positive direction of 490.0 newtons is equal to weight, and the only force acting backwards is the normal force, or excuse me, is the tension in the rope, and that's the same tension as the other side. Okay, so I should have labeled this earlier. I'm going to go ahead and label that last equation we found equation 1. Now I'm going to write the summation of the forces in the y prime or the x prime direction. So the summation of forces in the x prime direction equals, in this case, it's a big M, so I'll write the big M over there, times A in the x prime direction. In this case, this means 490.0 newtons plus negative tension is equal to 50.0 kilograms times A. And again, because I set this x prime pointing down on the right, the A on the right is the same as the A on the left. I'm going to call this equation 2. You'll notice that we have a positive t in equation 1 and we have a negative t in equation 2. So just like we did with the Atwood machine last time, the smart move is to add the two. So add 1 and 2, and what you get there is 490.0 newtons minus 34.300 newtons is equal to, now that was plus t plus negative t, so those just canceled out. When I add the right hand sides, I get 7 kilograms times A plus 50 kilograms times A, so that's just going to be 57.0 kilograms times A. So I can figure out that A is 490 minus 34.3 is 455.7 newtons. That's one extra sig fig divided by 57.0 kilograms. So divided by 57, and that gives me 7.9947 meters per second per second. So that's our acceleration. And I did it with numbers this time, so maybe that'll help you. Now I can plug A equals 7.9947 meters per second into, in this case, I'm going to plug it into equation 1 because that one has the positive t. And when I do that, I get t minus 34.300 newtons is equal to 7.00 kilograms times 7.9947 meters per second per second. So T is actually going to be equal to, I take 7 and multiply it by 7.9947. And that gives me 55.96. And now I've got to add 34.3 to that. So plus 34.3, that gives me 90.263 newtons. Now, the 7 times the 17.9947, that only had 3 sig figs, so that was only good to one decimal place. And the 34.3 was only good to one decimal place. So when I added those two, only one decimal place was significant. So I got 90.2 newtons for the tension. Anybody have any questions on that? All right, I didn't get all the ones that I wanted to get solved, but I think I got a lot of the harder ones, and that was the most important thing. It's now 6:40. Please chat me your first and last name if you haven't done so already. Again, that's what I do for roll. You guys are free to go, and I'll wait here for the last person to leave in case you have any questions. And don't forget your test, everyone. Test by Sunday. Test next week's a face-to-face. I'll update the syllabus and post that by tomorrow.
Professor, I have a quick question.
Yes, ma'am.
Just out of curiosity, do you know if they're gonna offer physics 242 in the summer?
Yeah, they almost always do. I can't. The only time we wouldn't is if we don't get enough students. But yeah, we offer a 242 and a 241 every summer.
Okay, great. Thank you
Hey,
so much.
no problem. And it's
Have a
usually
great
me,
day.
by the way. So sorry about that.
Oh, what was that?
I said it's usually me that teaches it. So sorry about that if that
Oh, no,
wasn't what
that's
you're shooting for.
okay.
Well, thanks.
Have a good night.
You too. See you, Brianna. That looks like it. Looks like no one else has any questions. Hope this was helpful. And let me stop sharing, and then I will say bye bye, bye bye. Oh, up. Got to see the minion up here. Yes. All right. Now I'll say bye bye. Don't forget your test. Online test due Sunday, 11:59 p.m. Face-to-face test due next week for you online classes. Our face-to-face students are taking them on Wednesday of next week. So keep an eye out for your updated syllabus as well as for your practice test for the second online test and the actual online test. Bye bye.